welcome everyone. Thanks for coming. And on behalf of Kathy Whitlock, who is the director of the Institute on Ecosystems, I really welcome you here today. Kathy's in Brazil, so she was unable to attend, but she's, I'm sure, thinking about us right now. So, welcome. And Perry Miller is leading off the IOE Rough Cut seminar this semester. He's a professor of sustainable cropping systems, and he's in the LRES department. And Perry joined the MSU faculty in 1998, so he can probably tell us the history of the university over the last 10 years. He specializes in semi-arid crop rotations with an emphasis on dryland wheat systems, and he was recently named a fellow in the American Society of Agronomy, which is a great honor. And he's also a member of the Canadian Society of Agronomy and the Crop Science Society of America. So thank you, Perry, for presenting your work here today. Thank you all for coming, and I hope that you'll regularly come to the seminar series this semester every Wednesday from 12 to 1 in this room. Thanks very much.
And I just want to remind you we're recording it, so I know lots of you have attended, but when you question and answers, please touch the front of the mic till the light comes on green, and then we'll hear your question on the recording. Thank you.
Thank you all for coming. I'm actually new to this venue because I have one semi-sacred wellness activity that I do once a week, and it's Wednesdays at noon. So I'm giving it up, though, today for you guys. I've got this image up here because when I started at MSU in 1998, I came from southwestern Saskatchewan, just across the Montana border to the north, doing actually very similar research, and I started I think I accepted the job in October 97. I would drive back and forth up that highway between Swift Current and Bozeman, and I'd always see this sign, Think Rain, and it just, I mean, at the time I didn't realize how much that sign was going to come to mean to me, because we were about to tangle with droughts that I had never tangled with before in my young research career. So I'm going to ask this question, can we manage long-term climate variability? And a key word for me is variability. I'll talk a little bit about trends in climate and how that might relate, but it's the variation that I'm really interested in. So keep that in mind. Here's I think it's a relevant example. I grew up hunting deer in northern Saskatchewan, and we get these die-offs periodically from tough winters. You know, so as you might get, that's an exaggeration, but you know, we do actually get very severe die-offs, and so it makes for poor hunting. And I came up with this graph that was a deer mortality index based on cold temperatures and snow depth. And basically, if you get to a 10, that's the kind of years where we have significant die-offs. And the point I want to make here is that there's some variation, right? We vary along this line. We get these red bars every once in a while, but they almost seem regularly spaced out. About every 6 years, we get one of these real bad winters that cause, you know, it's not perfect, but it's that variation that matters to me in hunting, and it's the variation that's going to matter also in farming. So what I'm going to tell you about today, I'm going to talk about some trend line effects. I'm going to share some data with you from Luther Talbert in the Plant Sciences Department relative to spring wheat. I'm going to show you some Iowa data from Jerry Hatfield. I want to talk about a regional cooling phenomenon from the Canadian prairies. That's pretty interesting. And then I want to connect some of that climate variability to ag. My mantra is probably to fallow or not to fallow.
I don't know how to keep
Oh,
sorry.
I don't think it'll be a huge problem on most slides. And then we've actually had a chance to interact with producers on this topic. And so I'll share you a little bit about what we learned with that, and then I hope to have enough time to finish off on a soil resilience note. So this is a slide from Luther looking at optimal temperature for growing spring wheat at different plant stages. Those numbers in red are the actual temperatures in 2012. And so considerably above optimum. It was a real tough year for growing wheat. In Montana, that was actually the year that most of the USA discovered that water mattered, even in corn-based systems. Luther and Susan Lanning have done wheat variety testing for a long period of time in Montana. And one of the cool things is they've kept a variety common. Since 1950, this variety Thatcher has been present. And so that raises some interesting possibilities about looking at plant growth over a long period of time. This, I don't know how many of you are familiar, but that's our network of research centers out in the state. So that's what all those different dots are. And that's where they did this wheat variety testing. They looked at some temperature trends over time from 1950 to 2008 and annual temperatures rising. But it was the March temperature, the spring temperature, that was really interesting. And that's this bottom line here, the one with all the wiggles around it. A lot of variation, despite a fairly strong trend of warming over time, over that almost 60-year period. Well, in my world, March is going to mean planting dates for spring wheat or other crops. You know, the warmer it is, the earlier I can plant, and that's probably a good thing. But July temperatures is actually, and rainfall is probably what I think more about. It wasn't hugely significant in here, but it was. And as it gets warmer, it makes it a lot harder to grow these spring crops. They noted no change in precipitation. They weren't the only ones to see this. This is a paper in 2001. Joe Caprio was retired from our department at that time, but looking at lilac bloom and stream pulse. But again, look at the variation. You know, there's a trend line through this, but there's a lot of variation. Another paper out of southwestern Saskatchewan, I was working, that's out of the research center I was working with at that time, Herb Cutforth put out a paper, again showing that late winter, early spring period has warmed over the last 50, 60 years, again with some variation. So this is back to Luther's work. One of the things they've looked at is how planting date has changed over time, right? This is Julian days on the y-axis, and then years across the bottom. And in these trials, where they're trying to do everything right and optimally, they've gotten earlier and earlier and earlier over time. Why is that? And it's a negative correlation. So as the March temperatures have increased, they've gotten earlier with their planting. And as they've gotten earlier with their planting, they've gotten higher yields. I guess it kind of blocks out a little bit on the bottom, doesn't it? But the bottom line is warmer Marches give us earlier planting, and earlier planting leads to higher yields. And because they have had this variety constant for 58 years, they were able to see that. But there's another aspect, and that's July temperatures, and that's what usually hurts spring crop yields. So the warmer the temperature, the lower the yield. In this case, the test weight is even more significantly affected. Test weight is the last yield component that's formed in a crop's development cycle. So usually if you've got an end-of-season insult of some sort, it's the one that gets affected the most. Significant at 3 of these 6 sites across the state. So, you know, there's a problem, obviously, with lower yield and lower test weight with higher July temperatures. For this particular slide, I was interested in that heading date advancement over that 57, 58-year period, getting earlier by about 1/10 of a day per year over time. And doing some figuring between variety development, because they had this variety that was constant over all that time, and agronomic management, about half of that earliness was due to earlier planting, and about the other half was just due to earlier varieties, earlier maturing varieties. That wasn't conscious selection, right? That's unconscious selection. They're selecting for things that yield the best. Things that were earlier yielded better. Then you can get into sawfly. I mean, how that affects the timing of sawfly flights, I'm not even going to go there. But it has other biological implications. This is the major pest of wheat in Montana. And so, when Luther gives this talk, one of the things he says is he's worried he's going to put himself out of business, or that this climate trend is going to put himself out of business, because one of the ways to beat a warmer summer temperature is to plant more winter wheat. Well, Luther's a spring wheat breeder, so that's potentially a problem. I don't think that's actually going to happen anytime soon. But one of the things he's developing are plants that will tolerate warmer temperatures, and so they're having some success with that. I'm not going to get into that. My point is, though, we could shift cropping practices to try and respond relative to that trend line. So another example of a trend line is Iowa. So we're talking corn now. I got to see Jerry Hatfield present this talk at our American Society of Agronomy meeting in November, just a few months ago. This is some work that they've done with their regional climate cap project. In this particular slide at Des Moines, they're showing over a 41-year period, a 3 degrees temperature rise, but more importantly, a 12% rise in atmospheric vapor content. And what is that causing? This is from the National Climate Assessment. that came out recently, and roughly over about a 60-year period also, an observed change in heavy precipitation. You know, here's Iowa, right? So they're in an area that, and heavy precipitation, by the way, is defined as more than 1.25 inches in a day. So for most Montanans, that's hard to understand, but that's, and so, you know, northeastern United States is facing a lot of that right now, apparently. Here's the slide, though, that's really interesting. This is information that what they did is break up the precipitation in the growing season into 2 periods. I'll call it the spring period, May and June. You can call that spring or early summer. And in the late summer or summer period, July and August. And all they did was, you know, a biplot with inches of water received in July and August versus inches received in May and June from a pretty big time period, 120 years. And they were able to put a 95th percentile around where all those points were falling. Here's 2012. Remember that record dry year that caught most of the Midwest off guard? Unusually dry spring and dry summer, but the interesting thing is, you know, wet spring, dry summer over here, a couple of wet cycles. I mean, how many of these years recently are falling outside this 95th percentile? And I'd like to know better if this same sort of phenomena is happening in our northern plains region, but interesting. And that probably does reflect a trend line more than variation. You know, implications for practical farm management. Here's a graph showing the relationship between inches of water received in April and May and the number of days that you lose in the field, right? You can't plant when it's wet. You can't be out there spraying when it's wet. There's things you can't do when the soil's wet. It's almost 3 days for every inch of rain that you receive. So if you're getting wetter during this period of time, that's probably going to cost you or make you less timely in a number of operations, and that can have real economic costs. I think about crops, but there's a whole animal side that I don't even begin to think about. You know, if we're getting, this is a stress chart for dairy animals, humidity in this direction, temperature in this direction, so if we're heading this way, probably not very good from a livestock perspective. And I'll come back to livestock when I talk about this brief interaction we had with farmers at a stakeholder workshop, because we had both ranchers and farmers in the room, and the ranchers seemed to get this more than the farmers did. I'll tell you about that in a minute. Last trend line example I'm going to show you is this land use change example from the Canadian prairies. And a little bit of summer fallow is just the practice of taking an entire growing season and keeping it plant-free over that growing season so that you can conserve water for the next crop. So essentially you give up a year of cropping in order to store a little bit of water to get into the next crop. So it's been very important to the history of the Northern Plains. Without summer fallow, the farming systems we have wouldn't look the way they do. Well, what's happened with summer fallow? This is a figure from 1926 to 2007. Looking at aggregate summer fallow area in 2 Canadian provinces and 4 U.S. states in the semi-arid northern plains. And it peaked somewhere in about 1971 and has been in free fall ever since. And there's really strong economic reasons why summer fallow is being abandoned. You know, basically where you can get enough annual rainfall, you will. There's pretty strong economic pressure to walk away from it. And it's actually below 4 million hectares now in this region. There's north central Montana. Over a period at that time, it's blocked out, but 1995 to 2000, well, it's actually 1998 to 2012, I think, on that chart. Not even in our region, doing this, where everybody else around us is in free fall. Why is that? That's actually one of the things that drives my research program, because summer fallow is the single most harmful thing you can do to soil. It's the single least sustainable practice that we have. So I think a lot about ways that we can try and alter that summer fallow area. Well, here's an interesting thing. In the Canadian prairies, there's a paper that came out that documented summer cooling and wetting as a result of getting rid of this summer fallow over a 25-year period. But you know, we're talking 60 million acres of cropland up there. If you get rid of fallow, you're affecting that footprint in a very, very big way. And essentially their argument was that if you have bare soil, so they were assuming tilled fallow rather than no-till fallow, but if you have bare soil, you change the balance of sensible and latent heat flux in such a way that you get a thicker boundary layer. And the thicker this boundary layer, the less likely it is to rain. On the other hand, if you plant, if you have a crop growing, and it's important to note this was just for a midsummer period that they were looking at. I'll give you the punchline on that here in a second, but this is in the middle of the growing season. If you have a crop there, you end up with a much narrower or thinner boundary layer, much more likely to rain. If it rains, it's cooler, that sort of thing. So this is real. It's been observed. It's over a 25-year period from mid-June to mid-July, temperature dropping almost 7 degrees Fahrenheit. So we're used to trend lines going like this, but here's a regional example where it's actually cooled. The T-min versus T-max is actually narrowed as a result of that. And the big thing is rainfall has increased 1 inch over that 4-week period. Most guys in Montana would kill to have 1 inch during that time of year. Now that's somewhere between 5 and 7 additional bushels of wheat. So if we can do it there, could we do it in the triangle? And that's a question Paul, I know, is wrestling with. If we build it, will he come? It seems like it would be a huge gamble, but I know of another example in South Dakota where they said the same thing has happened. So it would be nice to have that trend, but now I want to talk about the variation associated with that. Because I think that's so overwhelming in the semi-arid region that no matter what that trend line is doing, that variation is probably 10 times more important. And also just, I guess for full disclosure, being wetter and cooler in the middle of the summer in the Canadian prairies isn't necessarily a good thing. Because this is an image that's actually been too common in the last decade. This happens to be in the Assiniboine River in eastern Saskatchewan, but there's been a lot of flooding going on in recent years, which is not a good thing. And I don't put these on for comic value because this is real money. When you get an implement stuck like this, a $300,000 tractor, and how you torture and yank on that thing to get it out of there, that's probably a $400,000 sprayer. There's 2 backhoes. You can use the arm to try and crawl yourself out of the mud. Well, there's actually a cedar just out of the picture that they were trying to use these backhoes to get out. So, and that's. Those pictures are all over the internet, so it's been happening. It's been too wet. This is an area I took this picture in 1997. The reason I put up there, it shows a road closed sign, right? There's a gravel road that's flooded over, and that's in the dry brown soil zone of Saskatchewan. Saskatchewan has this very colorful way of describing their agroecological zones. They have the brown soil zone, the dark brown, and the black. And that relates to historical organic matter, right? Organic matter is black, so the darker you are, the wetter you were. Then they have this place called the dry brown soil zone that's just north of the Montana border, between a set of hills and the Montana border. So that's, brown's already dry. I don't want to be dry brown. And yet here's flooding going on. And during most of the time that I was working in southwestern Saskatchewan, there was flooding and excess moisture going on there at the same time that it was fairly dry in Montana. So over a fairly narrow range, you can have that kind of temperature difference. So I want to show you this slide just to orient you to Montana in case you're not used to thinking about cropland precipitation. Basically, anywhere that's light brown, that's your wheat fallow areas. That's where you don't really have enough water to grow a crop every year. You get to yellow, it's right on a knife edge of whether it's economically viable to crop every year or not. And so this is what we call the golden triangle. That's 50% of our wheat production in that golden triangle. There's a lot of fallow in that triangle, isn't there? And it's about 42% fallow in any given year, so it's not quite 50-50, but it's close. Northeastern Montana, it's Mac Burgess put this slide together, and I like the way he put it. It's less dry, and they actually tend to get a little bit more timely summer rain. It's not as front-loaded as it is over in the triangle, so it's a little bit further out in the season. Makes spring crops a little bit more possible, and they have actually gone away from fallow. If I'd showed you a slide of northeastern Montana, it looks just like that larger aggregate graph. It's in free fall in that area. The Galton Valley, now I'm supposed to do research in the Galton Valley that reflects, I'm interested in this region up here, right? And so there is a little bit of brown that you can try to try and get something that's somewhat closer. It's still quite a bit cooler. So we actually spend a lot of time driving back and forth between Bozeman and the Triangle. Interesting to note, though, that our winters here in the Galton Valley are a lot wetter than the Triangle. Our summers actually aren't very different from the Triangle in terms of rainfall. They are cooler. Okay, so what about variation in rainfall? I'm involved in a project that looks at decadal scale variability in the Missouri River Basin. I'm a stakeholder advisory member, so I'm not very strongly involved. But I'm supposed to help, bridge some farmer contact and things like that. So we had a meeting in November of 2012 in Great Falls with some extension folks and several farmers and ranchers trying to explore this idea of what long-term variation in climate might mean to their particular agricultural enterprises. And so this is 2 graphs up here. Vikram Mehta is the lead on this project, and so he made this presentation in Great Falls. But this is June through August stream flow in the Missouri River near Great Falls over time, and you can see multi-year variation in that flow. This is the self-calibrated Palmer Drought Severity Index, which is just a measure of soil moisture. And you can see that there's pretty strong correlation between that river flow and that soil moisture. It's not perfect, but I'll show you some data here in a minute about how I struggled to do research when it was much drier than normal. It lines up pretty closely. Can we forecast this? There is that existing patternicity. If we could forecast it, it would be huge. So these multi-year precipitation cycles occur. Can we predict them? What would it be worth if we could? And that was the question we went in front of this stakeholder group with. But before I talk about that, I'm going to step back one more time and sort of share my personal experience with dealing with drought or multi-year weather phenomena. You recognize this is just a cutout, right? This is not the Pacific Ocean over here. So I've had people think that for some reason. I was in Swift Current, and I'm going to show you some research from Swift Current, and it was done at 2 locations, Swift Current and about an hour south of Swift Current. This is the triangle region I just showed you a bit ago, so I'm interested in how that research there linked up with that research. This is actually a seamless map that was developed by, Jerry Nielsen had a hand in coming up with this map. Actually, you were the U.S. lead on it, weren't you? A seamless Agro-Rico regional map. And so this Agro-Rico region number 12, has some commonality with the southern prairies and northern Montana, where 80% of our agriculture is. And so this is a study that was actually started by a wheat ecologist, Doug Dirksen, before I got there, and they were asking questions about recrop versus fallow and till versus no-till. And in order to ask those questions, they actually had to set up field sites 2 years in advance. So they're preparing things 2 years in advance, and then we wanted, the project was about alternative crops. And at that time, in the early 90s, southern Saskatchewan was a wheat fallow region. There really was not, any diversity to speak of. And so but we had a research station director who was somewhat visionary, and he really wanted to push this alternative crops idea. So in year 3, you grew these alternative crops, and then our final year, well, we should see what the wheat does on top of these alternative crops, right? This is our uniform wheat crop. Does it look very uniform? Looks like a banding gel or something, doesn't it? I mean, there's a lot of stuff going on there. Well, this study, they had some money, so they actually did this study 8 times, or at 8 location years, which there's not very often in agricultural research we actually get to do it, something of that magnitude. Looked at spring wheat yields, so they don't grow winter wheat there, so it's spring wheat. Bushels per acre here on the y-axis, and on different crop stubbles, which are these alternative crops. So we had 3 nitrogen fixes. This red line is wheat on wheat. So if you grew continuous wheat, which was one practice that was done there, this is the yield you would get of wheat on wheat. Then we had 3 nitrogen fixing stubbles, dry pea, lentil, and chickpea. And we had 3 oilseed stubbles, sunflower, mustard, and safflower. And the significant yield differences were on these pulse crops, or on these nitrogen fixing crops. And it was a 23% average yield increase. That's big. That's really big. And it was surprisingly consistent between the sites and among years. It really didn't vary that much. And it had a big protein boost on top of that. Pardon my froggy voice here. About a percentage point, again, on these pulse crop stubbles and not on oil seeds. That can be real money. That can be more than $1 a bushel in a strong protein market. So that was big. We had been told at that point we couldn't grow alternative crops, and if we did, they wouldn't give you rotational benefit anyways. So here's these 3 colorful soil zones I was telling you about in Saskatchewan. Here's the brown soil zone. That little green sliver is what was present for pulse crops at the time that study was begun in 1992. And here it is. This is actually 2009. The date is blocked out there, but that's 21% of that area is now growing pulse crops. It's huge. So that should be a simple thing, right, to jump down to Montana. We're not that far away. Should be able to replicate it down here. I was a little bit later in doing that study, 1999 through 2001. We looked at 5 locations. What this is, I've got a percentage here, or a proportion on the y-axis, and this is the proportion of a chem fallow plot. So we've got fallow plots replicated, randomized right within the study design. So we've got to measure what the wheat yield was on top of the fallow plot, and then we want to know what it is on top of all these alternative crops. And our alternative crops are pea in the green, chickpea in the brown, flax in the blue, sunflower in the yellow, and also on wheat in the red, so if we were going to do continuous wheat. This red line at 0.7, economists have shown us that somewhere around that point, you'd think you only need to get, when you have a crop fallow system, you're only getting a crop every other year, right? So it takes 2 acres to get 1 acre's worth of crops. So you'd think that line might be at 50%, but it costs a little bit more to grow a recrop, and so it actually turns out it's closer to 70%. So if you can get 70% of your fallow yield or better, you're making money. If you're not, you're probably losing money, and there's 2 sites there that are losing money. And where do you think those sites are? Here's Bozeman, this is Denton in central Montana. Here's Havre in the triangle, and this one's Dutton in the triangle. Not even close. That was quite different from what we'd seen in Saskatchewan. Another piece of the pie that's relevant here, this is the crop precipitation measured right here at our post farm. I started studies out there in 1999, and 2 inches short, 3 inches, 3 inches, 3 inches, 7 years in a row, we're short on water. I mean, is that the way climate works? I didn't think that at the time. I thought it was more of a random sort of stochastic event, but there's patternicity to it. 3 bushels, that is, 3 inches, that's 5 to 7 bushels per inch of wheat. That's $4 to $8 per bushel. That's big money. If you're short of water, it costs you a lot of money. Things finally turned around, and then all of a sudden we're at average to better than average rainfall. This pattern was parallel to northern Montana in that golden triangle. I mean, their drought was during the same time, and they were coming out of it at the same time. But they continued at average to better average than water, where we had a couple of wild cards thrown in there. 2012, a record drought. I think we were the only county in the state to get disaster relief that year. And then we got 2013, which was our second worst drought ever. So the variation is what kills me, right? That makes it really difficult to deal with. I want to show you what happened to Montana pulse crop production. I came here in 1998 thinking it would be an easy thing to get pulses grown in Montana. Did research for 6 years and got nowhere. We had a little run at them with chickpeas here at this point, but that disease got in the way and that killed that. What happened here? That was a change in the Farm Bill to change the risk structure for pea and lentil production. And it wasn't a huge change, but at that point they had no risk coverage, similar to wheat. And so there was some small price protection or price risk protection that was entered in the fall of 2003. It took a couple of years for growers to really catch on. Hey, this is actually helping us manage our risk. It's not just the growers, it's their bankers too. I mean, they've got to convince them that growing peas or lentils is a good idea, and the banker has a say on that a lot of times. So all of a sudden we had some significant pulse crop production. 4 counties in northeastern Montana. So the wettest, coolest area of the state grew some pulses. Now all of a sudden, 2009, it starts increasing again. That's when it started to rain, right? Remember when I showed you when that rain started flipping over from drier than normal to wetter than normal? So now it's spreading around the state. So there's about 700,000 acres. We're going to go back to a dry cycle. History's going to repeat. What happens then? This is some work that Mac Burgess did in a paper during his PhD, and this is a yield monitor visual showing the yield of wheat on wheat versus wheat on I think it was pea stubble. Yes, pea stubble in this particular case. A 6 bushel an acre difference, and when you're talking in a 20 bushel range, that's a big percentage. I think farmers are seeing how these pulse crops benefit their wheat production, and so I don't think we'll abandon pulse crops if we go back into dry cycle. They get this, you know, that there's real rewards to management. So I think we'll be okay. That's the paper that appears in. So what about climate adaptation strategies? I mentioned that land use change idea at the start. Maybe if we could just have a policy that encouraged everybody to go away from fallow in the triangle region, would it start to rain? I don't know. We did have a stakeholder workshop in Great Falls, and one I mentioned, and I will say coming out of that broadly, ranchers and farmers have very different management concerns related to primarily precipitation. And that, I think, as a plant person, that relates simply to the fact that ranchers are interested in perennial vegetation and farmers are interested in annual vegetation. And that's a profound difference in the way they use rainfall. Ranchers also have this additional thing relative to livestock welfare. So they've got a living creature out on the land that needs to survive and gain weight. But as we're interacting with these guys, the ranchers seem to get it. I mean, what we're doing, we're asking them, saying, hey, if we could predict that you're going into a wet period for 5 to 10 years versus a dry period for 5 to 10 years, how would you change your management? That's the question we went to them with. And what do you think the response was? You can't tell us what's going to happen next week. How are you going to tell us what's going to happen over a month? So it was kind of a no-sale approach. But that sounds more defeatist than I mean, but but then as we really had to prompt them a couple of times to say, hey, you know, really, you know, what if we could do this? How would you change your management? Well, then the ranchers were the first ones that came to the conversation. And I'll show you why that in a second. But we're talking about, you know, things that have real investment horizons or time periods that match investment horizons that would really matter to producers. This is another image from Jerry Hatfield. They're wrestling with the same concept in Iowa, where they're looking at variation in climate on, you know, seasonal to yearly to multi-year, all the way to decadal kinds of scales, and they've got this whole wheel of a calendar of all the kinds of decisions that a producer has to make relative to growing that crop and investing in land, and so there's ways that different time span of forecast could interact with investment decisions. Well, here's a simpler one in Montana. The brown line is our cattle herd over from 1998 to, I think this was 2012. And it's been fairly stable. The green line, though, is the one that matters from the climate perspective. That's our tons of forage. And when that green line gets very far away from that brown line, that is a big, big problem. That means you're trucking in low-density feed over some distance that's at a high value. You're losing money, almost certainly, on the sometimes hand over fist on the cattle side. You know, when the green line's above the brown line, that's okay. So these guys would really like to have some control over this kind of variation. The interesting thing with perennial vegetation is it's pretty much directly tied to water use, right? If you get an inch of water, you're going to get so much biomass. It doesn't work quite so cleanly with grain production because there's that extra grain formation step. But with perennial vegetation, it's a pretty clean reflection of how much water you get. Chad Lee, by the way, we had an economic development officer with Montana Department of Ag that put this slide together. And some of the next ones. Unfortunately, he's in a new portfolio now. He was really doing a great job there. So when we asked these ranchers what kind of changes they might make, there was 3 general things. Stocking density, I mean, that seems kind of obvious. If you had more vegetation, maybe you put more or less concentration out there. But some of the things under feed supply management, I didn't realize that these things existed. I didn't realize you could have multi-year hay purchase contracts, you know, to help stabilize some of your risk. There's different ways to manage your hay inventory, perennial versus doing some annual types of forage. The very type of forage crop that you select. This is a decision that's common on a lot of Montana farms. Do I plant this ground to an annual forage or do I plant it for grain? If I've got livestock, that's a very real decision I've got to make. And if I knew whether it's going to be wetter or drier than normal, that would probably impact strongly what I would do. You know, what could you do with capital investments? You could cross fence. Why do you cross fence? So you could rotationally graze, use your forage more efficiently, get more out of what you do have. Water efficiency developments. There's a lot of flood irrigation with forage production in Montana. The least efficient way to irrigate. maybe you upgrade that, maybe you invest in irrigation. Hay equipment purchases, there are ways that you could improve your hay management to make sure you make better use of the land that you have. And then back to, herd size and age management. Do I start selling off animals? What do I want to do? And so, like I say, they sort of got it. Then we went to the farmers. And I would say this is mostly from us because we really didn't draw this out of the farmers. We were trying to think about the sorts of things, the kind of decisions you would make. And so this crop rotation intensification, that's basically the fallow question I'm asking. Do I crop that land every other year, or do I crop it every year? That's what I mean by intensification. And so if I knew I was coming into a wet period, I could have a significant opportunity to harvest more cash crops. And some guys will tell you that it's a bigger deal to miss an opportunity like that than it is to get caught by a drought. I mean, there's these recent years where it's rained and we've had good prices. Rare opportunity to get ahead. I mean, that just doesn't happen. Matter of fact, this one, the length of it is unprecedented. Wet periods, from a soils perspective, which is one of the things that we work on a lot. If I could grow more vegetation more often, I could build organic matter. Organic matter helps manage soil water, so that's all good. Well, what about if I'm drier than normal? I can also come back to soil organic matter because maybe I can't grow that grain crop economically, but I can do things with cover crops and not use soil water and still invest in that soil organic matter, which is going to help me down the road manage soil water use more effectively. Obvious things with crop selection, irrigated hay acreage. This is a cash crop. And there's all kinds of, this is the part that interested me. If I want to go out and buy a new air reel for a combine that'll let me harvest lentils, what is that going to get? $75,000? I don't know. It's a significant investment, and so I need to, if I knew I was going to be wetter than I probably do that. So the point is that variation, right? That's what I really need to know in order to make smart investment decisions. So then, again, I told you we tried to convince these farmers that maybe we could, be successful with this prediction. Of course, that's yet to be seen yet. I got to sit in another session at the ASA meetings this past November, and one of those sessions was on modeling, global climate modeling. And one of the things I learned, that I actually already knew this, is that temperature is much easier to model than precipitation. And some of the take-home points I took out of that was that precipitation is much more difficult to model locally, and so that matters a lot, because we're trying to do things at a field level. And the overall assessment seemed to be there was some demonstrated skill. By skill, I mean accuracy. If they predict something, did it come true? There was skill at predicting precipitation in the winter time across much of the planet, and in certain coastal areas, closer you were to the ocean. Well, I'm in the northern plains. I'm a long ways from the ocean, and I'm on the other side of some big rocks, so that's the problem. And in the tropics, it was good. But this was one quote that really hit home with me. And I don't know if that's accurate or not, but it was by a credible scientist at the time, that we can't predict precipitation anywhere on Earth in the summer. That's not very helpful. I want to leave on a more positive note. Soil resilience, I think there's one other way we could, or not one other way, but another way we could go after managing climate variation, and that is by improving our soils and making them more resilient during various climate insults or variation. I'm going to show you quickly here. It's going to be a real schematic of a study that we started right here near Bozeman. Began in 2003. You'll see some fallow treatments in there. It's at a location where we really wouldn't need to summer fallow, but because I want to learn what happens with fallow relative to the triangle, that's why we have so many fallow treatments in there, because it remains a recalcitrant practice up in the triangle. We might have been a little bit ahead of ourselves committing to pulses over long term, because you'll remember, 2003 they still weren't doing anything, but they did take off after that. And Rick Engel helped. He's doing the soils stuff on this particular study. I do the crop stuff. He wanted to look at nitrous oxide emissions and did that for a couple of years. He confirmed that legumes in our environment were not a problem. He also confirmed that fertilizers actually weren't a big source of nitrous oxide. But again, remember that was during those drier than normal years, so we probably should go back and look at that in a wetter time. And he's got soil carbon data coming, he tells me, next month. So I'm really curious you'll see from this next data, we've built up the soil nitrogen supply power in these soils by including these legumes in there. But what I want to be sure is I didn't strip down the soil carbon in the process. So I really want to see what those soil carbon numbers look like. The unique aspect relative to this long-term study is we managed it at 2 nitrogen rates. So I'll show you all the rotations here in a second, but keep in mind that every one was managed at what we call a full recommended nitrogen rate, and that's 3 pounds of nitrogen per bushel of targeted wheat yield. 3 pounds per bushel of targeted wheat yield versus half of that. And we've had such interesting results, we are actually repeating this on 2 sites up in the triangle, 250 miles away. We're doing a pretty good job of staying on top of that, but it's harder when you're a long ways away from the study. So this is the study. There's 9 systems in there. I'm really going to concentrate on 6. Our base system was this tilled fallow. So I'm leaving tillage in the system at this point. Tilled fallow wheat. I've got spring crop phases and winter crop phases. So over 4 years, this is what that looks like. Then I take away the tillage and I go to no-till. So now all I'm doing is managing the fallow with chemical instead of tillage. Same rotation. Then I take away the fallow. And so now I'm going to continuous wheat and growing spring wheat and winter wheat. I'm not going to talk about this system. We added diversity with oilseeds, but we actually changed that system at one point. So we've got these systems that all were designed to include pulses. It turned out that we've really stuck with peas. We've never actually grown any other type of pulse. This one, we grow the pea to grain and then grow wheat in alternate years. System 6, we harvest as an annual forage, and system 7, we create what we call a pea manure, where we just spray it out and leave it rot on the soil surface. So all that vegetation has the possibility of ending up in the soil. So that should be our biggest contributor to soil nitrogen, and it has been. Actually, we had some short-term research that was encouraging us to maybe removing it wouldn't matter. It was all about what was going on below ground, but it turns out it does matter. And then we've got an organic system in there and a perennial system. And what's interesting about this one is we managed it as a CRP contract for 10 years, and now we've gone back. So we'll have some soil organic carbon data from that, and the early indications were that we had gained most significantly in that system. Now we're going back to system 5, or we're already 2 years into that. So now we're going to crop it again, like a lot of farmers are doing, walking away from CRP and seeing how that changes that soil organic carbon. So it's sort of a stepwise, and again, full and half rates of nitrogen. Why, I don't know if that would be clear to you. Why would I vary that nitrogen in that way? When I apply fertilizer nitrogen, I'm trying to target a specific yield. So if I'm going to do 60 bushels of wheat, I need to have 180 pounds of nitrogen in play. But what does that yield of wheat, that 60 bushel of wheat yield, what does that depend on? That depends on rainfall. And I don't know how much it's going to rain. And so if it's wetter than normal and I had a 90 bushel yield potential and I put that same amount of fertilizer on, I'll be under fertilizing it. If it doesn't rain as much as I thought it was and I have a lower yield, if I have a 30 bushel yield, then I'm way over the top on it. So that's why we do those 2 rates, because it is an uncertainty. It's a given uncertainty because we don't know how much it's going to rain. A very quick summary of nitrogen management, because I usually get quite a few questions on this part of it. We do measure soil nitrate N only to 2 feet. Actually, we've measured it deeper for various reasons, but relative to nitrogen management, we do it to 2 feet prior to seeding the wheat phases or any non-legume phase. So we know each time we plant how much nitrate is present. Relative to the peas, this is maybe more for farmers. We are using a good, a marketable semi-leafless green pea for system 5. For system 6 and 7, we use more of a cowboy pea. It's a leafy pea with smaller speckled seed coats, more consistent with that system. And then we do this thing called nitrogen credits. When I measure that nitrate, like I said we do, often if I go and measure after the pea harvest versus wheat harvest, I don't see any difference in the nitrogen that's in the soil. It's basically been used up, but I know that legume, based on research is why I know, that legume is going to release more nitrogen throughout the next growing season. So how do I estimate what that is? And there's been lots of debate in the farm world about how to do that. I go with a flat rate. It doesn't seem to matter how much pea you grew the previous year. There's no sort of mass balance approach. It's a presence or absence sort of thing. And so we take a credit of 18 pounds of nitrogen, which means we would reduce our fertilizer by that amount if we grow the peas to grain, or 36 pounds if we did it for forage or manure. And we've actually still been taking too much nitrogen off, so we've just raised those to 27 and 54 in our new. And then Anton Beckerman was able to bring a dimension to this in terms of a sort of a full-on economic analysis that I could never have done on my own. There's a lot of detail here, but I want to point out this stuff in blue here. He generated some real-world wheat protein discount premium schedules based on 42 Montana elevators over a 12-year period. And so that's another big uncertainty for us. We don't, in any given marketing year, you don't know whether protein in wheat is going to be worth money or not. And it's just about 50-50. And so that let us look at the returns from these trials in two different ways, with very sharp protein premiums or insensitive. Just a reminder what the weather looked like. I mean, we had good total annual precipitation during the first 3 years of this cycle. There's that record drought at 10.3. You know, in a year like 2010, look at our June rainfall versus July. That's not really a great thing. And that was actually happened to be in the spring crop phase. It did better than I thought it would, but I think some of these pulse systems really came into play with that real strong haying. It's called a haying off when you grow a lot of vegetation and you can't actually turn it into grain. And so this is, you know, there's lots of this. I'm going to show you one more slide after this, but this is the sum total of that economic analysis. And what we did was sum up net returns from each of these. Here I'm just showing you 6 systems. These are the 3 what I call wheat-only systems. The 2 with fallow in them. Here's the till fallow, the no-till fallow or chem fallow, continuous wheat. Here's my 3 pea systems. This one I grow pea to grain, pea as a forage, pea as a manure that just gets sprayed out. These are the summed returns over 4 years. So we do all the costs and returns for those crops for over a 4-year period in a very detailed manner. This is returns to land and management ignoring crop insurance is basically the way to say that. So you'd have to divide those numbers by 4 if you wanted a yearly return. And then I can create these 4 different scenarios, right? I had the high nitrogen, the low nitrogen, because I don't know how much yield I can expect, or I don't know how much rain I'm going to get. And then I've got these 2 different protein schedules, one that's flat and one that's steep. So that gives me 4 different scenarios that I can look at. Now, one of the things you notice is that these pea systems are falling directly on top of each other. Incredible resilience. You know, we're getting, when we're drier than normal, it gets into more detail than I could probably convey at this point. But, you know, in the wheat-only systems, especially when I under-fertilized, you know, low nitrogen, and had a steep protein discount, you know, these systems really start to spread apart. That didn't affect the pea system so much because it had, I guess the simplest way to explain it is it has a pool of soil organic nitrogen that it can rely on. It makes it less reliant on the fertilizer that I apply out of a bag. And so, whoops, well, yeah, here's a good, this is the way we'll finish it. This is actually the grain nitrogen yield ratio. So I'm just looking at sort of the total protein harvested in the grain between 2 systems. System 6 was, in this case, was the forage system. So we regroup peas, but we removed it as forage. So the roots are there, the shoots aren't. And then System 2 was the chem fallow. And so I wanted to know was what the grain nitrogen yield ratio was between having that pea forage present versus you know, no plants during the plant fallow period. In the first year, we got an observation every other year because it was the way the rotation was set up. First year, we actually had poorer growth following that pea forage. It improved. We harvested more nitrogen the second time, even more the third time. Even this was a critical year. 2010 was a very wet year, and we had a lot of chlorosis happening in the plots, a lot of nitrogen stress. But these pea-containing systems hung on to their nitrogen, built their yield, built their protein better. There's my record drought year, though. But that's probably a good thing because I didn't need the nitrogen in that year. Right, because my rainfall was down, my yield potential was down. This is the trick to explain. I try to tell farmers that soil nitrogen cycling is auto-tuned. I've got these 2 sources. I'll back up a step. Nitrogen comes from 2 sources to feed that crop, right? What I fertilize out of a bag, synthetic nitrogen, or what comes out of the soil. What I've done with the pulse system is build up that soil nitrogen pool. So I'm making it less reliant on the fertilizer that comes out of a bag and more reliant on what goes on in the soil. Well, that soil, it turns out, is conditioned by soil moisture. When I get wetter, I get more nitrogen mineralized out of that soil nitrogen. Well, that's when I need more nitrogen because my yield potential is higher. And the converse is also true. When I'm drier, I need that nitrogen. And that might not sound like a big deal, but if you guess wrong and fertilize at a full rate and don't meet that yield because it's too dry, in actually three different cases, we have had lower yields where we fertilized more because you get this hanging off phenomenon. You grow too much vegetative growth, it can't be sustained, the yield crashes, and you get very low yields of thin, barely marketable wheat, and I got less yield. Probably not a good thing. So this being more reliant on this soil nitrogen in the soil, I think, is a really critical aspect, and I think that is, that's tied naturally to climate variation. And I'm going to end it there. There's some acknowledgments, and I think there's a couple minutes for questions.
Could you briefly, if you can, explain a little further that pea manure process they use?
Sure, and that's a good. A pea manure is a type of cover crop. It happens to be a legume or a nitrogen fixing cover crop. So it's a type of cover crop that if I can grow that legume to some immature, not mature, immature plant stage where it's highly decomposable, I'm hoping that a bunch of that, both the shoot and the root, will decompose and end up in that soil and contributing directly to the soil nitrogen pool. And so nationally right now there's a huge emphasis on cover crops generally. It's more cover crop polyculture, but we work mainly, and we're doing some of that, we're checking out some of that stuff now too, but we work mainly with these legume-only cover crops. And the interesting thing is that it costs me money to grow that legume manure, right? The seed is $20 to $30 an acre. I've probably got $20 an acre, well, maybe not $20, $15 an acre in spraying it. I was managing it in not a very smart way initially. I was fertilizing it, fertilizing my pea manure. I probably didn't need to do that with a broad spectrum of PKS. That was $20 to $30 an acre. Point is, there's a lot of things that are costing me money to grow that pea manure. It better be building that soil in a positive way that gives me more benefit to the wheat crop, or I'm going to run a negative number. Well, you saw the economics. I mean, it did work out. Once we got that system equilibrated, didn't happen right away. It probably takes at least, we're in a wetter climate, I'll say it takes at least 6 years or maybe 3 cycles of that peas to get the soil changed in that way. And that's been shown in a couple other long-term studies in this region too, that there's a delay. It takes time to change that soil. So it's not a practice that's widely used by farmers, but some are doing it. And right now NRCS is promoting this cover polyculture in a pretty aggressive way. And we've got some work underway on that's so far the early indications are that the legumes are pretty important within that mix. We're looking at different functional groups.
How much of the nitrogen that's going in as roots, and how much is on top? Seems like the roots would be extremely efficient. What's on top? You might lose a lot of that.
No idea.
Harvest that and feed it?
I mean,
has Rick or anyone looked at the volatilization from that top material?
Rick has in a couple of instances and hasn't seen very much. So I mean, I did some short-term work, Tad, where we actually didn't see any difference between removing the shoots and not removing the shoots. So then I ran around and say, hey, you can take the forage and have your cake and eat it too, sort of thing. Mm-hmm. But in this study, this longer-term study, it has mattered. In this environment, clearly we're getting more nitrogen release where we've left the tops present to rot on the soil surface. But in terms of this thing is something I've run so low cost. The only reason we can run long-term studies like this is because I can go annually to grower groups and say, hey, here's what we did last year. Will you fund us one more year? And so I do that every year. I got to do that dance, go back for one more year of funding. But it's a way of getting a long-term study done, right? Because there's no USDA grant that's going to take on a 10 or 12-year-old. But as a result, the trade-off is I can't ask for very much money. And so I don't. It's there. If anybody wants to look at these dynamics, it's there if anybody's got money to look at it in more detail. So Klein has actually been very helpful at trying to think through some of this stuff. We haven't probably measured it as well as we should have, especially for root versus shoot kinds of things.
Why don't we just start charging more for crops instead of increased variability in climate, or convincing all farmers to say, that this is uncertain. I guess this is a really naive question. I don't know what controls the pricing and all that.
Well, the pricing of the, you know, I could put Joe on the spot here or somebody, but I thought, you know, from a policy incentive, there's probably things we could do to manage that risk. But I mean, the prices are set on a global basis, and that's supply and demand. Would you add anything to that, Joe? Or
You got the crux of it.
yeah.
So it's really difficult. I mean,
Well, I think it could be done, but it would take a concerted effort that, hey, this is what we're trying to do. And I think some of the, I mean, with the NRCS incentives right now, they're paying some fairly handsome incentives for people to try cover crops for 3 years on up to 450 acres. It's a pretty, you know, it's something that would entice you to try it. So at least, you know, they're trying to go that way. Now, I don't, and there is a conservation stewardship program where if you enroll in that and say you're going to cover crop, you can get some payments out of that. So I think the Farm Bill is evolving to more that way. So it's probably more possible to do this in the U.S. than it is anywhere else in the world because of the Farm Bill, I would. Adam?
Thank you. It seems like selling the long-term benefit over what's going to get you money in the bank soon is always a little bit challenging, and maybe there's differences there between leased and owned land, but I wonder, speaking to some of the other things that motivate farmers with the pulse crops, following up on this, are there opportunities to spread the workload out a little bit with the pulse and get the benefits and have them have to do the work at a time of year they're not busy?
That's a great question. I mean, anytime you diversify, you hopefully make better use of your machinery by using it at different time periods. It turns out, unfortunately, that your pulses often want to be harvested about the same time your winter wheat does. You know, you got an early maturing spring crop versus a winter wheat crop that matures early on. So there is a bit of a time. It's not as helpful as what you think. And as on to the long-term benefits, there are growers who get that. Matter of fact, I was in a conversation with a guy yesterday because we did some short-term 1 year of cover crops on his land and also monitored what he was doing in his field, and we showed that he had a pretty substantial yield loss. I think he lost 18 bushels to the acre of barley, and lost protein, which didn't matter in barley. But he was right back. I mean, you've got to keep looking at this in the long term. And I said, well, I don't have the funding. Well, I could donate thousands. You know, it wasn't in tens of thousands, but that's interesting, right? Because that's a farmer for profit who thought it was, you know, he thought we're getting the wrong answer, and he's probably right because we're only able to take a short-term look with a 3-year grant. He wants us to continue doing that over a longer period of time. So it's on me now to try and find some funding that would let us do that in a longer-term way. So I think if they believed or were convinced that it would happen, they would. There are some guys at least who would be willing to invest in that. Not all, obviously. I don't know majority minority.
Is there anyone else looking at the long-term benefits that could be related to increased critters, worms, soil structure, things like that would have a long-term benefit? It comes on slowly.
Well, certainly in the bigger picture of U.S. agriculture, there's lots of people looking at that. Not in a major way. You know, Klein has done some tack-on studies. We've had some students go out there and look at some soil microbial assessments. We went and did an earthworm census one time. That's hard work. I don't think I'll ever do that again. So yeah, I mean, I guess that's one of the reasons I talk about these studies is, hey, it's out there. You know, we do control access because we need not to mess up the crops, but we do allow people to poke and take samples and do minor things out there if they can help us learn about this system. Yeah, we're probably not doing a good enough job of that. See by the clock on the wall. It's 1 o'clock. Thank you.